Great. Thank you, David, for the very nice introduction. And thank you to David and to all the organisers of the seminar for the invitation to speak here. It's a great honour to speak at this seminar, and I think this is a very nice seminar. I've made, I should say, I've made my screen big, which means I can't see the chat. So if anyone wants to comment, please speak to me out loud, and I can hear you. So I'm going to talk about braid groups, presentations, and generalizations. The first thing I should say is that the slides will be available at my website. The link's up, but it doesn't work yet. But after the talk, I will fix this, so you don't have to rush to write something down if you're someone who likes to take notes. And okay, I'm going to talk about braid groups. And okay, how do I annotate? So whenever I use Zoom, it takes me a minute or two to find the controls. I know there is a way to annotate things. Okay, maybe I'll start and try and work it out as I go along. So I want to, at least for some parts, use a question and answer style to try and explain some of this maths. And I want to ask, what are braids? And I don't want to give a rigorous definition, but I want to draw a picture. So I can't see how to animate. Maybe I'm going to open another file where luckily I prepared a file which I was going to share. Okay, so now I think hopefully you can see a slide with a picture.
Yes, very well.
Great. Okay, thank you. So braids are something like this. Right? We have some strings which are in space, and they might move around each other in interesting ways, which means they're tangled up. Okay, and these are the things we want to study. So I thought I should explain braids before I explain braid groups. So next question is, why are they interesting? Why would you want to study them? And this is one possible reason. Right? They can describe the motion of point particles in 2 dimensions in time. So I've drawn here this is meant to be some 2-dimensional space on the left with some coordinate axes and 2 points marked with X's. And then if you imagine a time coordinate on the bottom, we can move forward in time and look how these particles move in their space, and they end up at some possibly different positions. And then the motion which is drawn out by these particles in time gives us some braid in 3-dimensional space. So if you want to imagine a complicated example of this, imagine a football match where all the players and the referee are standing on the field. And during the match, they run around in various complicated ways, running around each other, never colliding exactly in the same space, but often changing their position. And then at the end of the match, when they blow the whistle, they'll be in some different positions. And this will trace out some complicated braid in 23 strings, or however many people there are. So you can imagine that studying this sort of motion might be a little bit complicated, and having good techniques can be useful. So if you don't like football and want something more practical or scientific, you might try to imagine some particles moving in physics. Okay, so this is at least one reason why they might be important. Okay, so we want to study them, and how do we do that? Well, we want to look for some structure. Now, I'm an algebraist, so I'd like to look for some algebra. And is there any algebra here? Well, no, there's not. I mean, we use some geometry and maybe some analysis to construct this. I mean, I didn't tell you how one might define a braid rigorously, but maybe you can imagine you can have some intervals and some continuous functions. Maybe it has to be increasing in time. You could come up with a definition of these things based on the calculus we learn in university. But this doesn't give us any algebra. This just gives us a set of possible braids. Okay, so we need to be a bit cleverer. So the first idea is we're going to fix our endpoints of our braids. Okay, so I'm now imagining time is moving downwards, and I'm fixing my 3 points at the top. I'm looking at this top left picture, and I'm going to move my braids going downwards. And you can see now there is some algebra. I can compose braids now. In the basis of any algebra, whether we do addition or multiplication of numbers or matrix multiplication, we always start with a way to compose things. And so this is good. We have a way to compose braids. This gives us some algebraic structure. And the way I've tried to do this in the picture is I've taken the braid on top, I've squashed it so it's half the height. And then I've taken the one on the bottom and also squashed it so it's half the height. And then I've stuck the ends together. And hopefully you can see that this gives you the picture on the right-hand side. Okay, so we have a composition of braids. Now, there are many more things you might want in algebra than composition. So let's try and ask for more. Do we have identity, inverse, associativity? And no, we don't. I mean, if you try to define an identity element, you'll see that this just doesn't work. This squashing process makes it very difficult to keep anything the same. Okay, but we can be a bit cleverer again. Really, we should only care about certain aspects of our braids. If we make some small change, then as I've illustrated on the bottom left here, I've just moved one of my strings slightly. This shouldn't really change the essential properties of the braid. So perhaps we should work up to isotopy. We allow these small changes, but not any change. So these two things on the bottom left should be thought of as the same. But on the bottom right, I've drawn two braids which are not isotopic and should not be thought of as the same. Okay, so this second change gives us more power. Now, is there any more algebra now we do this? And yes, there is. Suddenly we have a lot more structure. We now have an identity element just given by this these braids with straight strings running from one point to another. So if you try and compose this with another braid, hopefully you can see this won't change it now. You can move your strings so they look like it originally did. We can get an inverse just by some reflection in a horizontal line halfway down our braid. And the final one is harder to show rigorously, but maybe you can believe it by looking at some pictures. We also get associativity. So suddenly we've gone from having no algebraic structure to just having a composition to now having suddenly also identity, inverse, and associativity, which are all the properties you want for a group. And I mean, to anyone who's taken an algebraic topology course and seen the definition of the fundamental group, this won't be this will be familiar to you, right? This is exactly the same thing that happens there. So starting with these braids, which are very geometrical, we've constructed some algebra. Okay, so we get a group. This is the braid group on n strings. So I fix my number of strings, and then I compose. I have my inverses and so on. And the first thing I want to point out about this group is that it's usually infinite. Okay, if some people are more used to finite groups, some infinite groups. These are infinite groups if as long as we have more than one string. And the other thing that's worth pointing out is that this braid group surjects onto the symmetric group. Okay, so the symmetric group is the ways of permuting a certain number of letters or numbers. And if you just read where the braids go from and to, if I number the marked points at the top and the bottom, you can see how you get elements of the symmetric group. Right, on the left, I've just done a simple crossing of two braids and shown how this might go to the non-trivial permutation in the symmetric group on two letters. And on the right, I've shown a braid which shouldn't be thought of as the identity. Well, it's not the identity in the braid group, but is sent to the identity of the symmetric group under this group homomorphism. So one approach you might try to take now is to look at the kernel of this group, of this surjective group homomorphism, and study the pure braid group. But in this talk, I'm just going to stick to the classical braid group. But that's another approach one might take. Okay, so now we have a group, and we understand how it works, but that's very different to being able to write down elements, right? Braids can be very complicated. How should we organize them into some structure that we can actually work with and we can list? Well, the standard method is to use a very nice presentation called the Artin presentation, which was written down just over 100 years ago. So the idea is you choose some particular generators. So the generators I'm going to denote SI, where I runs between 1 and n minus 1. Remember, n is my number of strings. So I've done an example here. If we set n equals 5, so we have the braid group on 5 strings, then I should have 4 generators, S1 to S4. And I've drawn S3 by here. Okay, so S3, you leave the first 2 strings, just do the simplest thing. They go down to the corresponding endpoint. And then the 3rd and the 4th strings cross over each other, with the 3rd string on top, the 4th string going underneath. Okay, and then the 5th string is just left alone. So hopefully you can see why if we have 5 strings, we have 4 generators, because each of them uses 2 adjacent strings. Okay, so these are the generators in the Artin presentation. And it's a theorem that these elements do generate the group. So by composing various combinations of these generators and their inverses, you can get any possible braid. Now, you also want to know what the relations are. So there's the first one is relatively easy to see. If you choose 2 generators which are far apart, okay, so the strings which are involved in them don't overlap in any way, then it's quite easy to see that these should commute. You can move the braids and get the same element of the braid group. So here I've composed S1 and S3 in 2 different ways. And you can imagine sort of pulling the strings across to make these pictures look the same. So this is the commutativity relation. Of course, this doesn't work if I chose like S1 and S2, that wouldn't work. But for S1 and S3, it does. And for S1 and S4, for example, it would work fine. So this condition that the indices must be more than 1 apart is what we need. Then the second relation we need is, in knot theory, it's called Reidemeister 3. So sometimes it's just called the braid relation as well. If you haven't seen this before, it can take a bit of staring at. Some people can take this in quicker than others, I think. But perhaps a good thing to do to start is to look at each of the strings and just watch where they go on both sides of this equation and check that they match up. So you stare at the pictures and see that this looks like a relation you should have. And then you look at the algebra and see what it says. And you just take some generator and then the next generator with index 1 higher, and then the original. So you compose those 3 things, and then you swap the I and the I plus 1 on the other side. And in fact, this is all you need. Again, this is a theorem, which I'm stating but not proving. So this is the entire Artin presentation. And we can actually say it in a slightly different way. So I'm going to use this graph in the middle, which is in black and blue. This is a Dinkin type A graph. And it's got 4 vertices because I'm working with 5 strings. So I've decreased this number by 1. And this is because I have 1 vertex for every generator. And now, instead of recording, so I have these 2 relations, right? These Reidemeister 3 and this commutativity. And instead of checking how close are the numbers, I'm now going to interpret this by, are they joined by an edge in the graph? Okay, so there's the same information, but just presented slightly more visually. Yeah, so I guess I've said this out loud, but I should repeat. It's a theorem that the art in presentation is a presentation of the Braid group. So it does generate, the relations are satisfied, and there are no more relations than what you get by using the ones I've already told you. Okay, this is my introduction to Braid groups. Maybe this is a good point to pause if anyone does have any questions they want to ask.
So I have a short question.
Yes.
Do you always get dinking type A quivers, or other quivers also arise in different scenarios?
So today I'm gonna concentrate on the type A case, but you could play this game with other dinking quivers, or even other dinking graphs, or even other graphs.
Okay.
I mean, this is one of the nice things about the art in presentation. Once you have this, you can start investigating other types of Braid groups. So yes, that works, but today I'm going to not concentrate on it.
Okay, thank you.
Any more? Okay. So this is one presentation of the Braid group, and it's a nice presentation. But next question I'm going to ask is, are there any other presentations? So yes, there are. I mean, presentations aren't unique, but how can we find some? And I'm going to tell you one way. I mean, there's lots of ways you could do this, but I'm going to try and change the graph. And now this relates to the question we just had. That was well timed. One thing we could do is change the graph and get a completely different group. That's what normally happens when people take a different graph. They get a completely different group. But now I'm saying, is there a way to change the graph and change the generators to change the presentation, but keep the same group? Okay, so I'm asking a different question here, and I claim there is, and I'm going to explain it. And this comes from the theory of cluster algebras. Okay, so this is some part of maths that's relatively new, sort of. I mean, less than 20 years old, I guess, but has made lots of impact. And one of the ingredients in it is a way to change graphs. So we could hope that this might be relevant, and it will turn out to be. So but the thing we need to know is that we shouldn't work with just undirected graphs like I had before. I should work with directed graphs. Okay, so all my arrows point in a certain direction. In representation theory, we call these graphs quivers sometimes. So when someone fires a bow and arrow, they sometimes have like a thing on their back where they take the arrows out of. This is called a quiver, and so you call a quiver a collection of arrows. And I'm going to describe some way to change these according to a combinatorial rule, and I'm going to stick to the type A case. There's a general rule, but I won't explain. But the type A case is quite nice. So it's to do with triangulations of polygons. I want to start with a polygon with n+2 vertices and edges. Okay, so n is still the number of strings on my braid group that I'm going to be working with. So here I've got n is, what was my n? Okay, I've got an 8-sided shape, so my n is going to be 6. So I think I was doing n equals 5 before. I've now moved to n equals 6. So I start with an octagon. Again, I was going to draw you some picture here, but okay, I'll just talk through it. Is there some way to point? I don't think I can see a way to point that you can see. Okay. The point is, I start with my
We can see your arrow.
Oh, you can see my arrow. Thank you. That's really useful.
Okay.
Okay. So there's my octagon I start with, and I can choose any way to triangulate this. In this example, I've chosen a particularly easy way where I've chosen this vertex and I've drawn these lines to every other vertex, and now it's broken into triangles. Okay, but I could have chosen some other way. And what I do then is on each internal edge, so not the outside, but all the others, I put a red dot. They're going to be the vertices of my quiver, and I've numbered them 1, 2, 3, 4, 5. And then I want to put some arrows between these dots. So the rule is, well, if I have 2 dots that are on an edge, these edges should meet at a corner. I imagine sitting in the corner and looking out, and I want to draw the arrows going left to right. So this means they're going clockwise around my corner. And you can see that all my arrows are going sort of in a clockwise direction around this corner here. Okay, so that's how I choose my orientation. So I think this was in, okay, I'll say the next bit. Now, this is a way to get a quiver starting from a triangulation of a polygon. Now I want to show you how to change the quiver, change the triangulation and change the quiver. So what I'm going to do is I'm going to choose a particular vertex. In this case, I'm going to choose 3 for my example. And I'm going to imagine removing it, and so removing the edge. Okay, and this thing here is a quadrilateral. I've got a 4-sided shape, and it's cut in half by this diagonal. So I want to remove it and swap it for the other diagonal. Okay, let's do that. So the rules are at the top, the text at the top of the slide has changed. And my second picture, you can hopefully see that I've swapped the previous diagonal for this new diagonal. And now I just follow my rule again. Right, the arrows between 1 and 2 and 4 and 5 don't change. There's now an arrow between 2 and 4 because there's some corner that I can look out at to draw this arrow. And if you go around the other corners, you can actually see now I have 3 over there. I'm going to get this 3 cycle appearing. Okay, so this can seem quite strange the first time you see it, this notion of quiver mutation, and it can do quite drastic things to my quiver, right? It's created a cycle where there was none before. That's often that's a big change in a graph. This can seem like a strange thing, but experience has taught us over the past 20 years that this is an important thing in mathematics, important operation. Okay, oh, and I should say there's a general definition which only works with the quiver. You don't need the triangulation, but it's slightly easier and maybe a bit more fun to explain with the triangles, I think.
Excuse me.
Yes.
Why did you introduce the arrow from 2 to 4? Mm-hmm. It seems like it's an extra arrow. Or what? Yeah.
Okay. So I want to imagine. Okay. What? Let me try and draw something. Okay, I want a new share. Can you see like a notepad now? Yeah.
Yes.
Yeah. Okay. 4, 5, 6, 7, 8. So let me. Yeah, maybe this is easier if I draw it out. Right. So here is my triangulation. There. Now let me. Okay, so first, if I imagine standing by here, then I have these two edges touching this corner, and so I draw an arrow going left to right where I can see it. Right. Hopefully this makes sense. And the same thing by here. I'm in this corner. I draw an arrow going there. So now I go in this corner and I do the same thing. I draw an arrow going left to right. And now I go in this corner and draw an arrow going left to right. And now I go in this corner and now I have to turn my head round, but left to right will look like right to left, and it should look like this. And there are no more corners which touch two internal edges. And I think these are all the corners. Yeah, there are no more like corners I could put a green dot. Like if I try to use this corner here where my arrow is, my mouse pointer is hovering, this only connects to one internal edge and one red vertex, so there would be nowhere to draw the arrow to. Does this make sense?
Yes, yes. Thank you very much.
Okay. Right. Let's try and share back to the slides. Oh, wrong slide, perhaps. Okay, can you see okay? Yeah. Okay, tell me if you can't. Maybe that's easier. Okay, so this is the combinatorial procedure of quiver mutation. Right, and now I'm going to tell you how to get a group by a presentation. So I'm going to suppose that my quiver Q comes from this procedure I just showed you. Then I want to define a new group, BQ, by the following presentation. So again, I'm going to have a generator for each vertex, just like in the Artin presentation. And the commutativity relation, as before, will happen if there's no edge between my vertices. I'll have this Reidemeister 3 relation. Now, it's oriented, so I don't care if there's an arrow, then I have this. I don't care which direction the arrow points. But there's something new now, right? If I have a 3 cycle, an oriented cycle from I to J to K to I, and in fact, by this procedure, all the cycles I create will be oriented, then I get this new relation where I want to say cyclically commute. I mean, that's wrong because these have like I appears twice in the first one, but once in the second. But I sort of take a length 4 path in this length 3 cycle and take it the 3 different ways I can do it. So this so the thing to notice first is that if there are no cycles, then this gives me the Artin presentation. In the first example where I had the one vertex and I drew lines out from this to every other side, and I got just like a Dinkin graph with a sort of forward orientation, this would give me back exactly the Artin presentation. But now, but in the second example where I had some cycle, there would be some something different happening. And I think I've done that example on the next slide. Yeah. So this quiver in red is the quiver that I got, that I drew just now on the notebook and that I showed on that slide. And so let's go through the group. Well, we have 5 vertices. So we have 5 generators, S1, S2, S3, S4, and S5. And then there are 3 types of relations. On the bottom of the slide, I put these in the bullet points. The first one says various things commute. So S1 will commute with, it won't commute with S2, but it will commute with S3, S4, and S5. I've written just the first of those there, and there'll be lots of other commutations. For each arrow, I'll get a Reidemeister 3. I've written out the one between 1 and 2. And I have this single 3 cycle, which will give me these, actually these 2 relations here, right? It will give me this first equality and this second equality. Okay, so this is this is my group as presented by generators and relations. Okay, and now you want to know something about this group. So I sort of told you what we were doing. But, here's the theorem. This is proved in joint work with Marsh a few years ago. So if Q comes from the triangulation, like I described, then the group we get via this presentation is isomorphic to the braid group. So this really does present the braid group. And the proof's not too complicated, right? If you have the idea to do this, then you can probably prove it, especially if you can guess this formula. So the idea is that we just check that a single mutation or a single flip of the triangulation will preserve the group, will give us a group isomorphism. And the formulas for these are given by sort of partial conjugation, where we conjugate some of the elements but not others. And this really uses the orientation of the quiver. Right? I fix my vertex K that I'm mutating at, and then I look at, I do something different to the generators whose vertex have arrows going into K. And it really matters that they go into K, not out of K. So here is the place where the orientation of the quiver is used. And so that will give me a local isomorphism. And then there's some combinatorial results, some combinatorial theorem that says this procedure of flipping will give us all possible triangulations of a polygon. So putting these together, we get that, and I guess using the fact that this special triangulation that I showed you gives us the Artin presentation, we know that we always get the braid group from, the braid group is isomorphic to these groups. Okay, so this is, and I should maybe we had this question already about other types. So this theorem actually works in types A, D, and E. Right? This works for the simply laced Dynkin types. But again, today I'll stick to the type A quivers.
Sorry, question. What is Q again? I think I missed something in the last slide.
No, good question. Q is a quiver. So if I go back, here's the example. Like Q is the red quiver that comes up in either of these pictures. And so we choose a quiver Q, which is drawn in red. Then given Q, we define a group BQ by these presentations. And then the theorem says that for any quiver Q, which comes from an n+2 gon, the group we get is isomorphic to the braid group.
Right. So you're right. Okay. So you get a different presentation for the braid group on the end generators. That's the point. Okay.
Exactly. Yeah.
Okay.
Any more questions?
Yeah, do you have some kind of topological or geometric picture of this procedure?
Yes, I do. So great question. Thank you. So the next question is this question, right? Where do these come from? So you do, right? The first thing is sort of combinatorial. I've just given you some combinatorial rule, given you a formula, and then you can just check it works. So the first explanation is combinatorial. Then we do have some geometric explanation. Yes, I mean you can just look at the sort of generators given by braids between different points arranged in different ways in the plane, and try to understand how changing generators will change the presentation you have. And yeah, in the paper we do that, and we do that in type A. This is yeah, I guess points in on a disk, and in type D you need to use an Oberfold. But yeah, there's some. We give at least one way to interpret this geometrically. There's also a third way, actually. We interpret this using homological algebra, and for me, this is something that interests me, and this connects back to the first to the first part, right? I said we have this combinatorial procedure of mutation, which comes from cluster algebras, and a lot of categorical structure has been discovered behind cluster algebras, and we found a way to connect it to that more complicated categorical and algebraic structure. So this uses actions of groups on categories. So that's the next thing I want to explain to you. What is an action of a group on a category? So I guess if I was being very complete, I'd now tell you roughly what a category is. I haven't done that. I'm hoping most people have some idea what a category is. If you don't mind, my brief introduction is that it's some collection of objects with relationships between them. The classical examples would be something like, instead of looking at a group, we look at the category of all groups and all group homomorphisms. Now, this can seem like a very scary thing at first, and it is really. The category of all groups and all group homomorphisms is a very scary thing that we don't really hope to understand. But there are smaller categories which we can hope to understand. Right? If we look at the category of finitely generated abelian groups and all homomorphisms between these, this is a much more tractable category. So these are useful sort of from an organizational perspective, but more and more are studied as mathematical objects in their own right, and this is a powerful technique. Right? I mean, they're now even being applied in applied maths. So if you know categories, great. If you don't, I suggest for any mathematician, it's worth going away and trying to learn a little bit about categories. They're also lots of fun. Okay, so I want to come back to the question: what is an action of a group on a category? Because I'm claiming this gives one explanation for these new presentations of braid groups. So first, I want to remind you, okay, so the first half was going to appear first, and then I would display the second. I want to remind you what a representation of a group is. Okay, so this is a more classical notion. We have a vector space, and for every element of a group, we have a linear map. So maybe more concretely, you could think of a matrix, or a matrix indexed by the group element, and you want multiplying the group elements to correspond to multiplying the matrices. That's what this equation here says. So that's what a representation of a group is. And now what's an action of a group on a category? Well, we want to start with some category. And then, okay, so then we need a way to move between categories. So the way to move between vector spaces is linear maps. The way to move between categories is to use functors. Okay, so we have a functor for every group element. And we want composition of group elements to correspond to composition of functors. So here's the equation there, with the slight difference that instead of having an equal sign, I have an isomorphism sign. So it's more sensible to ask for natural isomorphism of functors. Okay, so this is something like a representation, but we have categories instead of vector spaces. And what are some examples of these? So the next slide probably has far too much information on it, but let me talk you through one or two important bits.
Is there a type, or do you mean a category in the second? So in your functor, you had a funct.
On this slide, sorry?
In the previous slides, so your map is going from V to V in the second.
Oh, thank you. Yeah, that is a typo. Thank you very much. I mean, I literally copied and pasted this and changed things, and I forgot to change this. Thank you. That should say C to C. Yeah, good catch. Okay, so let's look at some actions on categories. So the sort of categories I want to look at are the modules for a ring. And if we have a nice ring, we can hope to understand all of its modules or its finitely generated modules. And the first easy example is, suppose we have a group which is a subgroup of the group of automorphisms of the ring. Then actually we can use these automorphisms to change the modules, and and this does give us an action of the group G on the category of R modules. So this is a good first example to understand, but it's sort of not that interesting because, I mean, you don't really need to use categories for this. You already understand that the group acts as symmetries of the ring itself. You don't gain much by this more complicated perspective. But there are some observations which are useful. One is that this extends immediately to a larger category called the derived category. So this is some way of the analogy here is that to construct fractions, the rational numbers, we start with integers, and we just allow ourselves to divide by some integers. Like we invert some things, and there's an analogous procedure which lets us start with a category and invert some morphisms, and we get a new category. So we start from a category of chain complexes. These are the algebra of algebraic topology, and we build up lots of modules to give this new category called the derived category. And the one of the reasons this is interesting is because it can have more symmetry than our original category. Okay, so there are situations where the group where we have a group which does not act as symmetries of the ring itself, but it does act as symmetries of the derived category of the ring. So these are some important examples, I guess, of group actions on categories. And now, okay, in this talk, we're talking about braid groups. So braid group actions were studied by Seidel-Thomas. So they were motivated by homological mirror symmetry, which comes from string theory in physics. And there's this, mirror symmetry does, and then Kontsevich has this homological interpretation. I guess the point is there's this one situation in symplectic geometry where you have a category where it's relatively easy to see that the group can act. And then you know or expect that this is connected to another category from algebraic geometry where it's less obvious that the group will act, but you can use the equivalence to transfer this action. And they investigated this and came up with a quite careful and detailed theory of spherical twists. These are certain ways that certain functors, and these can be put together into actions of braid groups. So one example, which I'm going to focus on from their paper here, is they have an action of the braid group on some derived category of equivariant coherent sheaves on affine two-dimensional complex space, where these sheaves are equivariant with respect to some cyclic subgroup of SLC2, which acts naturally on C2. So, I said lots of words there which I didn't explain, but I guess the takeaway point is there are some categories appearing in algebraic geometry where braid groups act in this nice categorical way. And in fact, all these situations that were studied in this important paper are controlled by certain algebras or rings which come from type A quivers. So I like these algebras, and I like this theory, and I wanted to see if this could be generalized and pushed. So the next question is, if this all comes from type A quivers, is there a generalization of them? So, I mean, there certainly are to say type D quivers or something, but I don't mean that. I mean a generalization seems more like type A, but in some situation where you have algebras more complicated than just coming from quivers. And there is some generalization in Iyama's higher dimensional Auslander-Reiten theory. Again, these are some words which I'm not explaining, but there is some situation where some analogous quivers have occurred. And you might hope that we could use them to construct some new group actions, that this theory would generalize to this setting. And I claim that it does. So you can create some new algebras and some new groups. And what I want to do is just tell you about the groups that occur in the next step up in the case d equals 2. D is dimension, and where the classical situation was a one-dimensional theory in some sense. So now I'll stop saying words that without explaining them, and I'll go back to telling you about presentations of groups. Okay, so I'm going to fix some number m, and I'm going to define a quiver Q2m. Its vertices are going to be given by pairs of natural numbers where if you add them up, they're strictly less than m. So 0 is a natural number for me. And maybe have a look at this example first. 4 is the number to look at here. M is 4. So I want pairs of numbers such that when you add them up, they must be less than 3. So I'm allowed to have 0 up to 3, but I can't have, say, 2, 2. But I can have 2, 1, 1, 2, 0, 3, or 1, 1. And you can see all the vertices here I have. And so if ignore the green and orange bits for now, just look at the quiver. I should also add some arrows. So I have these 3 types of arrows which create lots of 3 cycles by increasing the first digit, and then if I'm going left by decreasing the second digit, or I can go sort of down like this by moving one from the left to the right. Right? So taking 2, 0, I have 2, 0, and I take away 1 from 2 and add it to 0 to get to 1, 1. So this gives me some quiver.
Excuse me.
Yes.
This looks like a root lattice for type A Lie algebra.
Mm-hmm.
Is there something like a connection there?
Yes, there is. Maybe I'll just say yes for now, and maybe and not try to say something specific. And maybe if you want to know more, I can try and say something more detailed afterwards. I guess this quiver is. I've given some combinatorial description, but you can build this using Lie theory, type A Lie theory.
Okay.
So yeah, this is a good spot.
Thank you.
Okay, so there's my quiver, and now I'm going to define a group. So I'm going to define a group, and again, I'm going to have a generator for each vertex element, and I'm going to have 3 types of relations: commutativity, Meister 3, and this 3-cycle relation that I showed you before. So in fact, these are exactly the same relations that I showed you when we had these other presentations of braid groups. Okay, so but the important fact is these groups are going to be different because I'm using different quivers. Okay, this quiver here, you'll never get this by triangulating a polygon. Okay, so I'm now allowing different quivers to be put into this, and I'm only showing you the case where d equals 2. In both, I guess actually in both situations there were ways to get more interesting and complicated relations by increasing dimension. But the quivers you're allowed to input into these sort of machines to produce groups are restricted, right? If you just put in a random quiver, you can't expect to get out a sensible group. So the fact that I'm allowing a much more general class of quivers here is important. Okay, so there's a way to define a ring or an algebra also using this quiver, and one can show that this group that I've just defined combinatorially does act on a category you can construct from this ring, a derived category. And I want to say something very brief about the proof, which partly because it helps explain this group a bit more. So let's go back to the picture of the group, and now I want you to look at these 2 parts which I've drawn colorful rings around. So the first bit in green, this looks a lot like a Dinkin diagram of type A4, right? And we know So if I just look at the 4 generators given by these 4 vertices, and I look at the subgroup they generate, I will get a type A4 braid group, which is a braid group on 5 strings. Okay, so, and there's lots of other ways to do this from lines, right? If you sort of take, one of these horizontal lines, perhaps you'll get another braid group. So there are lots of braid groups sitting inside this in the classical art in presentation. But also there's other braid groups sat inside this using different presentations. And if you look at this 3 cycle that I've put a ring around, this is something which is not classically of type A3, but is mutation equivalent to type A3. So this sits inside. So we have another. So I guess I'm saying we have another braid group, in this case a B4, sitting inside this group G24 in a non-obvious way. So this total group seems very different to a braid group, but it has lots of groups inside it which are isomorphic to braid groups, lots of subgroups which are isomorphic to braid groups, and even I mean, you can say something stronger in terms of presentations. So using these facts and some things we know about categorical actions, you can check that this group really acts on this derived category. Okay, what else can you say? Well, so here I've really used lots of words that I haven't explained. But the point here is that there was this situation for classical braid group actions where they act on some categories coming from algebraic geometry. They were related to 2-dimensional complex space and some cyclic group action. Well, you get a similar result happening if you now go to 3-dimensional space. And okay, you might not have a cyclic group, but you have some abelian subgroup of a special linear group acting. Okay, so the point of this slide is just for me to try to convince you that these groups that I've given to you by some presentation do appear, at least in one setting, in algebraic geometry. And actually, it's known that they turn up in symplectic geometry as well. They can I think they act on certain Fukaya categories that some other people have constructed, and there are other ways where they turn up in symplectic geometry. So these do turn up in some relatively sophisticated constructions in algebraic and symplectic geometry. But I think it's an interesting question whether there's some direct geometric interpretation of these groups. Like, can you the types of geometry that I was talking about just then are much more complicated than the geometry I started this talk with about, points moving in space. And I don't think these groups do arise as points moving in space, right? I'm not, and I can't say they definitely don't, but I don't think they do for some, partly because I haven't been able to do it, but also because for other reasons as well, I don't think they do, but I wonder if there is some geometric interpretation. And here I don't know the answer to this question. If anyone does have any ideas, I'd be very happy to hear them. Okay, and that's everything from me. Thank you for listening.